Good morning, students. Welcome to the class on Palladium catalyzed coupling reactions. In this class, we will discuss about Trost-Tsuji coupling reaction. What is Trost-Tsuji coupling reaction? Trost-Tsuji coupling reaction is a palladium catalyzed coupling reaction between an allylic system where X is a good leaving group, with a nucleophile in the presence of palladium. So the product will be nucleophile. There is also a possibility that nucleophile may couple here also, because allylic system will involve in resonance. So the nucleophile may couple here or may couple here, because the allylic system will involve in resonance. OAC is a good leaving group, and as far as Trost-Tsuji is coupling is concerned, OAC, allyl acetate, is the best for coupling. This is the nucleophile. As far as Trost-Tsuji coupling is concerned, palladium, tetrakis triphenyl phosphine palladium is the best palladium catalyst for Trost-Tsuji coupling. So what is the product here? It will couple, the nucleophile will couple here. Then we have this Cn and then CO2 Me. So this is the product. I'll give you some practice problems. This is a neutral condition. It is not a perfect nucleophile, but it is a neutral nucleophile, because these two groups are strong withdrawing groups. So we can easily pick up the proton here. So under the reaction conditions, nucleophile will generate, but we are not taking the nucleophile like this. So it is a neutral condition. So the coupling occurs here, allylic system, then it couples with this nucleophile. So here, one side we have nitro group, other side we have ester. Generally, this reaction occurs in an SN2 fashion. This reaction occurs in an SN2 fashion. The nucleophile will undergo nucleophilic substitution, bimolecular nucleophilic substitution. So whenever we have chiral center then we must remember that the reaction is an SN2, so it leads to inversion of configuration. But In this case, the inversion of configuration takes place two times. Inversion of configuration occurs two times. How? The first case, palladium will add. So that when OAC is leaving, palladium will add from other side. As I said, it may involve in resonance. So the coupling may occur here or occur here. So palladium comes from the opposite side. So we will observe inversion of configuration for the first time. And then the nucleophile comes, right? Then the nucleophile comes. Of course, nucleophile will also approach this molecule opposite plane from the palladium. Say for example, here OS is above the plane, so palladium must be below the plane. Then nucleophile approaches this molecule from above the plane. So again we will observe inversion of configuration. So that means in Trost-Tsuji reaction, we observe inversion of configuration two times. So as a result, the overall reaction is retention of configuration. The overall reaction is retention of configuration. Here, this is the nucleophile, malonate ester, dimethyl malonate. So here palladium approaches this allyl leaving group from opposite phase. So first when palladium is attaching, we will observe inversion of configuration for the first time. Then when nucleophile approaches this molecule, it obviously approaches from opposite plane for palladium. So again we will observe inversion of configuration. So double inversion leads to retention of configuration. So the Trost-Tsuji coupling reaction will lead to retention of configuration. I'll give you one more example for this. So this is the allylic system and this is the nucleophile, right? Yeah, when we look at this reaction, nucleophile will couple with this carbon. When we count the ring size 1, 2, 3, 4, 5 membered ring. Okay. As we know, these two groups are above the plane, so that means hydrogens are below the plane. So when we write the product, this is 5 membered ring. 1, 2, 3, 4, 5 membered ring. And on the 5 membered ring, we have this. Now, when you want to write the stereochemistry here, of course, it is the stereochemistry around this carbon will not change. So hydrogen will be below the plane. Here also hydrogen will be below the plane. As we know, Trost-Tsuji reaction leads to retention of configuration. So the hydrogen will be below the plane only. So as far as Trost-Tsuji reaction is concerned, identifying the leaving group allylic system and the nucleophile is important. So in this case, what is the nucleophile? It is a neutral system, right? So we have two carbonyls on this carbon. So that means this carbon is acidic carbon. The protons on this carbon are acidic carbon. So this is the nucleophilic center. Then this is the allylic system where OPH group is a leaving group. So 1, 2, 3, 4, 5, 6, 7. As we know, 7-membered rings are not that easy to generate. When we have a possibility for 5 or 6, better go for 5 or 6. If there is no possibility for 5 or 6-membered ring, then go for 7-membered, then 8-membered. See, for example, if this carbon couples here 1, 2, 3, 4, 5, then there is a possibility for the formation of 5-membered ring. So that means these two will couple with each other, then this will double bond will undergo rearrangement, then OR is a leaving group. So what is the overall reaction? The overall reaction is the 5-membered ring, and we have CO2Me as well as C5H11. Then here we have one vinyl substituent, right? This is the product. Now I'll give you a little extension of this product. When it is treated with sodium iodide under thermal conditions, what will happen? Of course, iodide is not a good leaving group, but because we are supplying thermal energy, forcefully we are substituting OMe with iodide. We are forcefully substituting OMe. No. Here it undergoes decarboxylation. It takes methyl iodide plus carbon dioxide. It is a decarboxylation process. Under thermal conditions, it is a decarboxylation process. This is the product. Now, it is treated with 9-BBN followed by chromium trioxide oxidation and then diazomethane treatment. What is the product? So what is the product here? 9-BBN attaches to the less substituted carbon. Chromium trioxide oxidizes this organoborane to alcohol first, and because it is a strong oxidizing agent, it further oxidizes this alcohol to carboxylic acid. Then carboxylic acids, when they are treated with diazomethane, they will be converted to esters. They will be converted to esters. So 9-BBN will attach here. Chromium trioxide will convert this into a carboxylic acid. Carboxylic acids, when treated with diazomethane, they are converted to esters. This is the product. This is a jet double bond. When it is treated with sodium diethyl malonate under Trost-Tsuji conditions, what is the product here? See, here we are using two nucleophiles. One is for Trost-Tsuji coupling, one is for substitution of leaving group. Okay, right. In this case, isomerization of this double bond is also possible. Isomerization of double bond is also possible. So one side O phosphate is a leaving group, O acetate is a leaving group. So both sides we will observe Trost-Tsuji coupling, At the same time, when palladium is attached here, it will involve in resonance. So the isomerization of double bonds are also possible. So the product is one side we have coupled malonate, other side we have coupled anion dimethylamine. So both sides we have coupled this and the double bond is isomerized to E double bond. So this is also possible. So we have coupled two nucleophiles at the same time. Another important aspect of Trost-Tsuji coupling is that we can use these reaction conditions for deoxygenation. Of course, we know Barton-McCombie deoxygenation, Barton deoxygenation, but where we use radical reagents. So instead of radical reagents, we can employ a simple reaction conditions for deoxygenation. Right here, you see this. We are using arsenic lithium, alkyl lithium reagent. It may couple. It will couple with. Sorry, it undergoes nucleophilic addition to aldehyde. It undergoes nucleophilic addition to aldehyde. So we are generating alcohol here. This is the product. When we use this, we are generating O minus. O minus will attack on this carbonyl because chlorine is a good leaving group. Chlorine will be leaving and we are converting this into a good leaving group. We are converting oxygen into a good leaving group. Generally what we do, we use Barton-McCombie reaction for deoxygenation. But instead of Barton-McCombie reaction, which is a harsh condition compared to this Trost-Tsuji reaction conditions, what we can do, we can employ Trost-Tsuji conditions here for deoxygenation. What we are doing, we are coupling this allylic system with a nucleophile. So in this case, what we will do, instead of a nucleophile, we will use ammonium format. We will use ammonium format so that the allylic position will be protonated. What will happen? When we are not using any nucleophile here. Instead of nucleophile, we are using ammonium format. So under this condition, the allylic oxygen will be removed. So this is a simple method for deoxygenation. It's a simple and better method compared to Trost-Tsuji reaction. Please write the product. Just remove this oxygen moiety and place hydrogen. That's it. Now we will discuss some additional problems on palladium couplings, preparation of disubstituted alkynes and enines. This is dichloroethylene, dichloroethylene. It is coupled with this alkyne, just 0.5 equivalents. That means only one side we are coupling it. Only one side we are coupling it. So Negishi conditions, what we are doing, we are coupling it with this, we remove this proton and we couple this triple bond with the double bond. Yeah, instead of, I don't want to write the product, I'll give the next reaction also. And then what we are doing, we are again coupling it with one more equivalent with a different alkyne, with a different alkyne. With a different alkyne. Then what happens? We are using 0.5 equivalents, 0.5 equivalents. So this is for coupling one side and this is for coupling other side. Okay. So the overall product is, of course, this Z configuration is not changed. And this can be further explored by reduction with the zinc. When we reduce this with the zinc, both the triple bonds will be reduced to cis double bonds. Both the triple bonds will be reduced to cis double bonds. Both the triple bonds are reduced to cis double bonds. When we do this same reaction strategy with the E dihaloalkene, we do get E double bond, right? So this is E, and because it is zinc, it is Negishi coupling. Which halogen will be coupled first? Iodine or bromine? Of course, iodine, right? So iodine is most reactive in coupling compared to bromine. So we do get this product. Then again we will repeat the Negishi coupling. So we will get E alkyne. So in the previous case we do get Z alkyne, dialkyne. Here we get E alkyne, dialkynes. This is again Negishi coupling only. This aqueous ammonium chloride is work up at the end of the reaction. Now n-butyl lithium will pick up the proton here. Then zinc will add, anion will attack on zinc. So we are generating organo-zinc reagent that will undergo Negishi coupling with this compound. So the product is, we are generating organo-zinc here. It will undergo coupling with the iodine first under Negishi conditions. Then it is treated with two equivalents of n-butyl lithium . then it is converted into organozinc, then it is coupled with, I need some space, please take this example. Right. So when we treat it with the two equivalents of butyl lithium, what will happen? It picks up a proton here, it generates a triple bond. Then again it will undergo halogen metal exchange. So it generates negative charge and triple bond. Then when we treat it with zinc, it generates organozinc that undergoes Negishi coupling. So here we are generating dialkane. Triple bond is already there. We are converting this into triple bond and then we are coupling it with OMe, and this side we have methyl.